So first day I will cover the hands-on training on the multifunctional large-scale density function theory and density function perturbation theory, that is RESCU software. So firstly, I will give you some brief presentation about the product and our company Nano Academy Technology. And after that, I will start the demonstration part. So in the first session, I will give you the idea about the software, like how you can calculate any properties through this RESCU software. And in the second session, you can do the hands-on practice. So if we talk about this impulse technology, so basically this impulse technology is based in Gurgaon, which provide nanoscale material and device simulation software, optoelectronics device simulation software, and cloud-based material simulation software. And my most valuable partner, that is Nano Academy Technology. So basically this Nano Academy Technology is a Canadian-based company who developed this nanoscale material and device simulation software, where you can simulate carbon nanotube, graphene, nanoribbon, fate, tunnel junction, crystal, molecule, based on density function theory, density function perturbation theory, and a non-Euclidean green function theory. And if someone want to work on optoelectronics domain, like some Perovskite, tandem, organic solar cell, thin film, OLED, then we have another partner, Fluxim, that work on optoelectronics application. And if anyone has any problem in your cluster, like suppose you have some SPG server, that is not good for the DFT simulation, then we can also provide you the cloud-based material simulation software, that is exabyte, so that you can run the job on the online cloud resources like Amazon server, Google server, and you can download your result from this online cloud resources. So these are three major partners that we are representing in India. So we have scheduled this hands-on training on the Nano Academy technology and its product. So I will focus on this Nano Academy technology. So if we talk about the company overview, so this company was founded in 2008 by Professor Hongo, Dr. Zhu, and Dr. Lee from McGill University. Basically, it was developed for molecular quantum transport that has been used around more than 10 plus years. And they enhance their feature for material development through advanced digitalization and modeling tools. Now they have also addressed the emerging sector of quantum computing revolution, that is QTCAD. So basically QTCAD is a TCAD software based on the finite element method, so that you can analyze the spin qubit devices in semiconductor. So we have several unique features and more development are released day by day. So basically they are located in Montreal, Quebec, Canada, originally from McGill University. So this is the company overview. And if we talk about the journey of the software, like from where the journal was started. So basically in 2001 from McGill University, where Professor Taylor and Professor Hongo, who developed the quantum transport package first, which is also supported by some Northwestern University in 2002. After several development in 2008, they have laid this foundation of Nano Academy technology, and officially this Nano Academy technology was listed commercial in 2009. So basically in 2009, they have developed the nanodical software, and in 2015, they have developed this RESCU software. So both nanodical and RESCU are the background simulation engine, so that you can define your DFT parameter, DFPT parameter, NEGF parameter through this background simulation engine. So apart from the background simulation engine, here you can see the graphical user interface is there. So this is the graphical user interface that is called Device Studio that will help you to do the modification, manipulation in your atomic structure, crystal structure, molecular structure, and device structure. And this Device Studio is a graphical user interface of the both Nanodical and RESCU software. Even recently, they have launched this RESCU Plus. So if you want to work on more number of atoms, then this RESCU Plus will be very helpful. So this is the journey of the software. So this is the general overview of our tools, basically both RESCU and Nanodical. So these are the two main brand of material simulation software. So they include a broad range of advanced method for simulating complex material property at different level. Also, they have the tool and toolboxes that can be used for effectively preparing the calculation, executing the calculation, analyzing the result that comes out from the atomistic simulation. So basically this RESCU is for the material simulation and this Nanodical is for the material as well as device simulation. So any material you can simulate based on the density function theory and density function perturbation theory from this RESCU software. And you can simulate any material, any device structure based on the density function theory and non-equilibrium green function theory from this Nanodical software. Now this advanced tool are there for building this structure. You can build your crystal structure, molecular structure, device structure, and manipulate these properties. So you can manipulate the alpha, beta, gamma value, ABC value, primitive cell, conventional cell, even armchair, zigzag, type of graphene, nano ribbon, nanowire, nanotube, grain boundary. So this advanced tool are there for building the structure along with the user-friendly interface. So that you can set up your DFT parameter, DFPT parameter, NEGF parameter, like electron temperature, cutoff energy, exchange correlation function, K-point sampling, iteration control, Spintronics calculation. So once you define all the parameter and you can click on the generate file so that this software will automatically generate your input file. So there is no need to write any script for any structure. Simply you can define the parameter and click on generate file. So once you do the simulation, you will get some output. And that output you can visualize from our visualizer. Either you can visualize in 3D view, 2D view, and 1D view. Here you can see these are the some material properties that you can simulate. Like you can simulate the electronics property, structural property, optical property, thermal property, magnetic properties, electronics and thermal transport properties, and electron phonon coupling. So the material property you can study from the RESCU software, and material as well as device properties like IP curve, photocurrent, transmission coefficient, Seebeck coefficient, thermoelectric conductance. So all this device property you can simulate from the Nanodical software. So if we talk about the bigger application of this software, like where you can utilize our software. So the bigger application of this software for the molecular structure simulation, molecular based device structure simulation, surface simulation, 2D material based device structure simulation, complex material like hexagonal, tetragonal, tri-black phosphorus material, interface between different geometry and different symmetry, and some carbon based material you can also study. Like you can create any molecule. It could be either organic molecule and inorganic molecule. So we have the molecular builder, like we have the molecule 2D builder and molecule 3D builder. Also, you can simulate any material based on the molecule. Here you can see these are the molecule and these are the electrode. So molecular based device structure you can also study, and also you can create any surface. Like we have the Miller indices, so you can define your combination ESKL value like 100, 101, 111. So whatever the combination you want to create the surface, you can simply create from our device studio. And then you can enhance their various properties from our simulator, that is Nanodical and RESCU. So these are the bigger application where you can utilize your software. So if we talk about the feature of this RESCU software, so in terms of accuracy, RESCU also cover all the steps in the accuracy ladder of atomistic simulation. So one of the main advantage of this RESCU, it cover all the accuracy ladder of the electrons in the material. Like we have the various exchange correlation function, like we have the LDA, GGA, meta GGA, hybrid function, like HSC function is also there. You can also include your Spintronics application, like collinear spin, non-collinear spin, spin orbit coupling. So these all parameter you can study based on the density function theory method. So in terms of analysis tool, so we have a very complete list of analysis tool. For example, here you can see this is the result of band structure calculation and density of state calculation with this RESCU software. So one of the main advantages is that they cover a few main basis sets that are used in method for the atomistic calculation. Here you can see this is the result for the band structure and for the numeric atomic orbital and the real space basis set calculation. And this is the very important part of this RESCU, which gives the user to ability to benchmark their simulation. So you can simulation against the different method and comes up with the very complete conclusion of this software. Like here you can see these are the analysis parameter. Like you can create any symmetry. You can also relax your structure, any device structure, any material structure. So we have the method, like we have the molecular dynamic, conjugate gradient, steeped descent. So these are the method that you can apply for the relaxation. And you can also simulate the band structure, band unfolding, density of state, like Phonon density of state, local density of state, Malkin population, and Wannier function. So these all features you can study based on the density function theory method. So we have a very powerful DFPT toolbox. Also, this is one of the main strength of this RESCU software. So basically by using this DFPT toolbox, we are able to calculate a variety of material properties that are based on the response of material, external perturbation theory. So basically this DFPT is a density function perturbation theory, so that you can calculate multiple properties like unclaimed dielectric constant, vibrational mode analysis, low frequency optical property, non-resonant Raman spectra, nonlinear optical susceptibility, electron phonon coupling. Like you can study phonon band structure, phonon density of state, boron effective charge, infrared intensity, complex, dielectric permittivity, complex refractive index, energy loss, oscillator strength. And for the non-resonant Raman spectra, you can also simulate the Raman tensor, susceptibility, intensities. And for the electron phonon coupling, you can calculate the EP matrix element, scattering time, and mobilities. So these all features you can study from this density function perturbation theory method. So here you can see, this is the example of DFPT toolbox, and we see this is the example of dielectric constant for the material which calculated with this RESCU software. So you can see this is the accuracy benchmark. So we can see that our result perfectly match with the experimental data, also with the numerical code. So this is the accuracy benchmark where you can compare our result from the numerical experimental data. And here you can see this is the performance benchmark of the rescue. So you can see that we can easily reach the system up to more than 400 atoms. And this is the very tough computational problem for other computational atomistic code. But with our state of solver rescue, we can easily calculate this system material up to 20K atoms. So for that, you need some EHPC cluster. So here we can see that this is the another example of DFPT toolbox. And again, this is the Phonon band structure and Phonon density of state simulated result with the RESCU software. So you can also compare our data from the experimental and also with the other numerical code and methods. So basically, you can also perform this kind of calculation for every atom that you have in your system. So you can see this is the Phonon density of state for the supercell diamond structure. So in this structure, we have supercell that contain 216 atoms. So here, this is the another example of optical property at the long wavelength based on the density function perturbation theory. So you can see this is the hexagonal aluminum nitride, and we can clearly see that from this atomistic simulation, we can capture all the main feature of the optical spectra. Like here you can see we have simulated the dielectric permittivity for the real and imaginary part. Also, we have calculated the refractive index for the real and imaginary part with respect to wavelength. Also, you can calculate IR intensity and oscillator strength based on the DFPT toolbox. So this is the classic example of this type of information that one can achieve from an atomistic simulation of the material. So here we see that this is the simulated Raman spectra of a silicon nanowire. So these nanowire are constructed from different phases of the silicon that contain 9R and 3C. So these are the different phases. So if you individually study these phases, then you see that the peak at the frequency which are different. So these are the frequency at the peak. So here you can see this is the simulated result of Raman spectra. And this nanowires actually the 9R comes with the smaller frequency and the 3C phases comes with the higher frequencies for this silicon nanowire. So this rescue is a real space electronic structure calculation. So this rescue is very state of art, general purpose, first principle quantum transport package, which combine both density function theory and density function perturbation theory. So that will allow computing all sort of response function like polarization, Phonon band structure, and optical properties. If we talk about the key feature of this RESCU software, so this RESCU software is written in MATLAB and C language, and it can focus on large scale system. So up to 20K atom you can easily simulate from this RESCU software. Also, this RESCU comes with the DFPT implementation, like you can calculate the dielectric tensor, dynamical matrix, optical properties like dielectric permittivity, refractive index. Raman tool is also there, so that you can analyze the tensor, spectrum, and intensities. Also, we have the advanced functional like the DFT plus EXX for the hybrid, and DFT plus U, that is for the Hubbard atom. So Hubbard in the sense you can define their ES-PDF combination. So we also include the common analysis tool like density of state, Phonon density of state, local density of state, projected local density of state, band structure, band unfolding, charge analysis, non-linear optical susceptibility, Spintronics application you can also study like collinear spin, non-collinear spin, spin orbit coupling. This software also comes with the Phonon tools for the finite difference-based method. And we have two methods of this DFPT. First one is Chebyshev filtering. Also, we have the Sternheimer. So this is the general information of this RESCU software. And if we talk about the RESCU Plus, so this RESCU Plus is written in Python and Fortran. And from this RESCU software, you can simulate the system atoms. So up to 100K atoms you can easily simulate. So this software comes with the Python interface. Also, this software includes the ion dynamic like relaxation, EMD, molecular dynamic, nudge elastic band, and all the common analysis tools like band structure, density of state, Phonon density of state, Malkin population, band unfolding, Spintronics application, and also you can see this is the Nanowire Plus. So from this Nanowire Plus, you can simulate up to 6 probe device structure. So not only for the 2 probe, so up to 6 probe device structure you can easily simulate. So thank you for listening this presentation. So you can see this is my contact information. So if anyone has any query related to the Nanowire RESCU software, so you can drop the message. Either you can also send us the mail so that we are ready to help you in your research application. Now I would like to switch on the demonstration part. And if we talk about the installation procedure, so I hope everyone get the mail. You can see we have forwarded this mail, and here the procedure are mentioned so that how you can download this software. You can see this is the download link. So whenever you click on this link, you will find this interface. And here you need to click on this download option. Select this download anyway. Then your file will start downloading. Here you can see it will start the downloading. So I have already downloaded this folder. So the zip folder will be downloaded. And once the file has been downloaded, you need to select that file. You can see this is the zip file. You need to select, right click, and you need to extract this file in the C drive. You can see this is the extract file. then it will take a little bit time. And you need to select the location in the C drive. You can see this is my C drive, and then you can click on this OK, so that it will start the extract. And once the file has been extracted in the C drive, you can see this is my C drive, and the file has been downloaded. You can go to this bin folder. Again, you can open the mail, and here you can see the license file is attached. So you can select this license file, right click, select this save as. You can choose the location where you want to save this license file. You can see this is my device studio. You can select this bin folder, and then you can select this save option. Here you can see we already I have the license file, so I need to replace. So you can select this yes, and then you can go to your bin drive. You can see this is my C drive, and this is the bin folder. In the bin folder, we have this device studio application file. So this application file you need to open. So you need to double click, and here you can see. So whenever you click and double click on the device studio application file, you will find this interface. So I would like to start from the scratch. So you can select this create a new project, select this OK, and here we need to enter the project name. So you can see this is my project name. Then you can choose the location where you want to save this project. Then you can click on this save option. Now you can see this is my project name. So basically this is the device studio, that is a graphical user interface of the Nanowire and RESCU software. So this interface will help you to build your structure. You can build a crystal structure, molecule structure, device structure, and then you can study their properties. Here you can see this is the project explorer where the input and output file will be shown. This is the property explorer where the property of a whole structure or individual atom you can see. And this is the job manager. You can see this is the menu bar. In the menu bar, you can see we have the file option. And in the file, you can see this is for creating a new project. You can open your existing project. You can save the project. You can design your new device structure, crystal structure, and a molecule structure. Here you can see this is the import option. So this software have two options to import the material. Either you can import the material from this local database that exists inside this software. Either you can import the material from the online database. If we talk about this import local, you can see this is my C drive, device studio, and here you can see this is the material folder. In the material folder, you can see we have 0D material, 1D material, 2D material, 3D material, and organic material. So this is the 0D material. In 0D, you can see we have the molecule like amorphous and crystalline molecule. You can see these are the amorphous molecule. And here you can see this is the crystalline molecule. So these are the crystalline molecule. You can see this is the 1D material. In 1D material, you can see we have the nanotube. So these are the different combination of Kroll vector, N and M value. Like also we have the armchair, zigzag. So any type of nanotube you can select and you can click on this open, so that you can easily import this material file in our device studio. So this is the 1D material, nanotube. And here you can see this is the 2D material. In 2D material, you can see we have the novelty material like arsenic, bismuth, black phosphorus, hexagonal boron nitride, and also we have the graphene. So this is the 2D material. Here you can see this is the 3D material. Like we have the conductor, insulator, layer material, magnetic material, metal oxide, novelty material, and semiconductor. Like you can see this is the conductor, pure metals, and these are 3D material. So these are the conductor, and here you can see these are the insulator. You can see this is the layer material, and this is the magnetic material. Here you can see this is the metal oxide. So these are the different metal oxide. Also you can see this is the novelty material. In the novelty material, you can see we have the perovskite based material. So these are the perovskite based material. These are the topological insulator. And these are the half value metal. So this is the 3D novelty material. And here you can see these are the semiconductor. So this is the semiconductor. So this is the 3D material. And here you can see these are the organic material. Like we have the crystal and the molecule. So the conclusion is that this is the material database that exists inside this software. So either you can import the material from this database, and also you can see this software support this file format. So if you have any file format like .sjw, .xyz, .cif file, .xsd postcard file, contar file, scf.input file. So these file format you can easily import in our device studio. And if the material is not available in this local database, then you can also import your material from the online database. So you can see this is the import online option. So here you need to enter the chemical formula of the material, and then you can click on this search option so that you can search any material. Suppose if you want to import some WSA2, you need to enter the formula and then you can click on this search option. So you can see these are the different combination of WSA2 with different space group information. So any combination you can select, And also you can see this is the symmetry information. Like this is the space group information. These are the ABC value. These are the alpha, beta, gamma value. And here you can see these are the atom and their Cartesian coordinate point. So as per your need, you can select this structure and select this add option so that you can easily import your material from this online database. And if the material is not available either in the import local option, either import online option, then you can also create your material from this new option. Like you can see, this is the device builder and this is the crystal builder. So if you want to create your own material, so you can see this is the crystal builder that will help you to build your crystal. Either you can design your simple structure, complex structure, alloy, any crystal you can create. Here you can see we have the lattice information, like we have the space group, like 1p1, 2p, 2p1, 3p2. So these are the various space group information. So once you select the space group information, then the Brevis lattice will automatically select it. Then you can also change the ABC value, alpha, beta, gamma value. You can also add any element from this add option. Also, you can change their fractional coordinate point. So whenever you want to add any element, you need to select this add option. Select this 0, 0, 0 fractional coordinate point. Then this default carbon element will be added. So if you want to change this carbon with any other element, you can double click and then periodic table will be open. So from this periodic table, you can select any element as per your need and then you can select this OK. Like you can see, if you want to select this aluminum, you need to select, then click on this OK option. Here you can see the carbon has been replaced by the aluminum element. Then you can also change the fractional coordinate point. Suppose if you want to create a black phosphorus crystal structure, so first we need to select their space group information. So I would like to select orthorhombic. You can see this is the orthorhombic Brevis lattice. Here you can define the ABC value as per your need. So I would like to take a default value for the A, that is 3.3136. And the same value I can define for the B, and here I can select the C value, 4.3763. So any value you can enter as per your need. If you want to change the B value, you can change. Like here you can see I would like to select 10.478. And here I can replace this aluminum with the phosphorus. You can see, you can double click on the aluminum and from this periodic table, you can select any element. So for the black phosphorus, I would like to select this phosphorus, select this OK. And here you can also change their fractional coordinate point. So if you want to create any structure, then you should know their space group information, their ABC value, the element, and their fractional coordinate point, so that you can create the structure. So n number of atom you can add from this add option. Like that. You can also remove. If you want to change any value fractional coordinate point, like you can see, this is the 0 value. Here, if you want to change, like here, I would like to take 0.10168. So this is the fractional coordinate point P2. Here, I would like to change this fractional coordinate point 0.08056. Then it will become a black phosphorus crystal structure. And once you design this structure, you can go to the preview style. You can show the primitive cell, either you can show the conventional cell. Like you can see, this is the primitive cell, and this is the conventional cell. So this information is for the black phosphorus. Select this preview, select this build option. So this is the crystal builder. And if we talk about this device builder, here you can see, this is the device builder. Like you can create any device structure, like left-right structure, left, center, right device structure, bottom and top device structure, bottom, center, top device structure, front and back device structure, front, center, and back device structure. So up to 6 pro device structure you can easily simulate from the Nanowire software. So the device simulation I will cover tomorrow. And if we talk about the molecule builder, so you can see this is the builder, and here we have the molecule 3D builder, and this is the molecule 2D builder. So you can see this is the molecule 2D builder that will help you to build your molecule. Either you can design your organic molecule, either inorganic molecule. In the left hand side, you can see these are the various fragmentation. Also, you can see these are the bonding option, like single bond, double bond, triple bond. So as per your need, you can design your molecule. Suppose if you want to design a benzene molecule, then first we need to select the ring segment. You can see this is the ring segment that has been selected, and then you can click anywhere. You can see this ring segment has been selected. I would like to draw the single bond from all the side of carbon element. So you can see these are the carbon element. So I can select this draw single, and you can draw the single bond from all side of carbon like that. So you can see, and as you know, for the benzene structure, we need only hydrogen atoms. So we need to replace all the CS3 with the hydrogen element. So we can do one thing, we can select this choose element option, and from this periodic table, we need to select this hydrogen. You can see this hydrogen has been selected. You can cancel this periodic table, and you need to click on the carbon so that it will be replaced by the hydrogen element. So you need to replace all the CS3 with the hydrogen element like that.
Hello, sir.
Yes, sir.
Sorry to interrupt. Can you show me this again? How to access this one? Like just 30 to
Which
40
one, sir?
second back. Like how do we start? This like I'm not able to get how you are able to get this where you are drawing the structure.
Okay, sir. Next, I will repeat it again.
Yeah, yeah, sure. Thank you so much.
Like you can see, this is my interface. So if you want to design any structure as per your need, you can select the fragmentation. So for the benzene molecule, I would like to select this ring segment. You can see it has been selected and you need to click anywhere. Like you can see, this ring segment has been selected. And for the benzene molecule, I would like to draw the single bond from all side of the carbon element. So if you want to draw the single bond, you can see this is the draw single. You need to select and you can draw the single bond like that. So every side of the carbon element, you can draw the single bond. Here you can see there is no CS3 because here the hydrogen has been selected. Now you can see this is our C6CS6 benzene molecule. And once you design your structure, then you can select this apply data so that this structure will be imported in our device studio. Here you can see this is our benzene molecule. In the toolbar, you can see we have the various force field calculation to minimize the structure. So if you want to minimize the structure with the help of force field calculation like UFF, GFF, GameCal, so as per your need, you can select the force field calculation and then it will minimize your structure. Now you can see this is our benzene molecule. You can also change the name of this molecule. Here you can see this is the rename option. Here you can enter benzene. So this is our benzene molecule. So this benzene I have created from this molecule 2D builder. And if we talk about this molecule 3D builder, so you can see this is the molecule 3D builder. And here you can see this is the add atom option. So this molecule 3D builder has extra advantage. Like here you can see you can import your molecule. So any molecule you can import and you can edit as per your need. So if you want to add any atoms, you need to select this add atom option and then this periodic table will be open. And from this periodic table, you need to select any element. You can see this carbon has been selected and these are the fragmentation. Like we have the single, here you can see this is the tetrahedral, this is the single atom. So this is the single atom, this is the divalent. So as per your need, you can select the fragmentation and you need to click in this dashboard. So this is the tetrahedral carbon element. If you want to design a complex structure, so any structure you can select from this add option. And here you can see these are the various toolbar. Like this is the modify bond. So if you want to modify the bond between any two atoms, you need to select two atoms. Like you can see this is the first, second atoms, and this is the modify bond interface. You can see this is the default none option. This is the draw single bond. So if you want to change any bonding option as per your need, you can select. Like this is the single bond, this is the double bond, this is the triple bond, this is the resonance bond, and this is the half metallic bond. So as per your research work, you can change. So here just I am showing a default, like how you can create this structure, and you can change their various bonding option. Either you can change various angle. You can see this is the modify angle. So if you want to modify the angle between any three atom, you need to select the three atom first. You can see first, second, and this is the third. Either you can enter the angle here, either you can drag and drop this one so that you can change the angle. Like you can see. You can also fix any atom. Like you can see this is the atom first that you can fix. Then only 2 and 3 will rotate. You can fix any atoms. So these are the various menu bar. Also you can see this is the dihedral. So you can change the angle between 4 atoms. And this is the add hydrogen option. So these are the various toolbar. And if you want to import any molecule in this molecule 3D builder, you can see this is the import option. So if you want to import this benzene, you need to select this open. So you can see this is our benzene molecule that I have created from the molecule 2D builder. So if you want to create any other molecule, like if you want to create a toluene molecule, then we need to change this hydrogen with the carbon, and also we need to add 3 hydrogen so that this structure will be toluene molecule. Like here I would like to change this hydrogen, this add atom option, select this carbon, select this single atom, and I would like to replace this hydrogen with the carbon element. Now you can see these are the this is the carbon and their fractional coordinate point. This is the hydrogen. So for the toluene molecule, we need 3 hydrogen atoms that should be connected from this carbon element. So you can select this add hydrogen. You can click 3 times, then 3 hydrogen will be added. And now you can see this is our toluene molecule. Suppose if you want to create a trinitrotoluene, we need to add the nitrogen group. So we need to replace this hydrogen, and this hydrogen with the nitrogen, and also we need to add the oxygen. So here you can see this is the add atom. I would like to select this nitrogen, single atom, and I would like to change this 3 hydrogen with the nitrogen. We need 2 oxygen so that it will become the nitrogen group. So we can select this add hydrogen. You can add 2 hydrogen here, 2 hydrogen here, and 2 hydrogen here with this nitrogen. And we can change these two, and these two with the oxygen. You can see this is the atom. We need to select this oxygen, select this single atom, and we can replace the hydrogen with the oxygen. And you can see this is our trinitrotoluene molecule. So once you design this structure, you can select this apply data. Also, I will give some time so that that time you can ask your queries. So basically, first I would like to show how you can create this structure and you can analyze their various properties. And in the second session, you can do the hands-on practice. So you can see this is the crystal builder. So this is the black phosphorus crystal that I have created from the crystal builder. This is the benzene molecule that I have created from the molecule 2D builder. And this is the trinitrotoluene molecule that I have created from the molecule 3D builder. And this is our W2SE4 crystal that I have imported from the import online option. So you can see this is the W2SE4. If you want to select only WSE2, then we need to delete these three atoms. Then it will become a single layer WSE2. So you can draw the rectangle, select the atoms. Here you can see the atom has been selected. And from this toolbar, you can see this is the delete atom. You need to click, then these three atoms will be deleted. So this is our single layer WSE2. We can also change the name. This is our single layer WSE2. And for simulating any material, here you can see this is the simulator. And in the simulator, you can see we have multiple simulator. Like this is the nanodical that is based on the density function theory and the non-equilibrium green function theory. So from this nanodical, you can simulate any material, any device structure. This is the nano scheme that is basically for the tight bonding model of nanostructure. Here you can see this is the RESCU software that is dedicated for the material simulation. So based on the density function theory and density function perturbation theory, you can simulate any material. And this is the RESCU Plus. That is the advanced version of this RESCU. So basically today I will cover this RESCU software. So you can see this is the RESCU. And in the RESCU, you can see multiple options are there. Like this is the self-consistent field calculation so that you can define your DFT parameter. So if you want to define DFT, you need to select the SCF calculation. And if you want to optimize any structure, you need to select this relax option. Like you can see, this is the relax that will help you to optimize your structure. Like you can see, these are the method. Like we have the quasi-Newtons, steeped descent, and conjugate gradient. So any method as per your need, you can select. You can click on this generate file so that the optimization input file will be generated. And then you can also run that input file to get the optimized structure. So basically first I would like to define some DFT parameter. You can see this is the SCF calculation for the crystal. Here you can see this is the shimmering sigma, this is the resolution, This is the method, like we have the real space and also we have the linear combination of atomic orbital. So these two methods are available. So as per your need, you can select the method and you can generate their file. Also, you can see this is the exchange correlation function. Like you can see, this is the LDA, GGA. Also, you can see these are the hybrid function, like hybrid GGA, HSC03, HSC06. Also, you can see these are the meta GGA. So any exchange correlation function you can select. Also, you can select the k-point sampling. So this is the basic setting. And here you can see this is the iteration control. Like this is the tolerance, like charge density, total energy, maximum SCF step, mix method. Like you can see this is the Poole. This is the mix variable like density, density matrix, potential. And this is the basis set. Like this is the arrangement by element. And you can see this is the LDA plus U. That is basically for the Hubbard atom. Hubbard in the sense, here you can see these are the atom and their pseudo potential file. Like this is the double zeta polarized. If you want to select this LDA plus U, then you will get the SPDF combination so that you can define their value. Here you can see this is the Spintronics application. Suppose if you want to include any spin in your material like no spin, collinear spin and general spin. So you can see this is the collinear spin and this is the maximum value. If you select this general spin, then you will get maximum, phi and theta. You can also change any value. And if you want to include the spin orbital interaction, then you need to enable this option. So here I would like to take collinear spin and I would like to generate the file. So basically here you can define your own parameter as per your research and then click on the generate file. So once you click on the generate file, you can see this is the WSET folder. You need to click on this arrow. Then you will find the rescue crystal folder. And then again you need to click on this arrow. Then you will find the input file. So here you will get the input and output file. Here you can see this is the property explorer where the property of a whole structure you can see. You can see this is the properties, like these are the vector value, vector A, vector B, vector C. This is the total number of atoms. So here we have the 3 atoms and you can see this is the total area of this lattice. If you want to show the single atom and their properties, you need to select and you can see this is the tungsten and their XYZ coordinate point. So once you generate the input file, if we talk about the script, so you can see this is the scf.input file. So you can select this file, right click, select this open with, so that you will get the script. So whatever the parameter you have defined, you can check out from this script. So you can see there is no need to write any script for any structure. This software will automatically generate once you define the parameter and click on generate file option. And you can see this is the atom dot xyz, so that you will get the atom and their Cartesian coordinate point. You can see this is the value of collinear spin. So for running the input file, you need to select the input file first, right click, select this run option. So if you want to run the job on the parallel, so we can provide you the cluster license. Like you can define the parallel core like 5 core, 10 core, 15 core. So there is no limitation of core. You can define up to 128 core. So the license that we have given to you is just for the education purpose, so that you can evaluate your license. So only single core you need to select. But whenever the user will purchase this software, then we can also provide the cluster license, so that you can utilize your core from this parallel option. So once you define all this information, then you need to select this run option. Here you can see this is our job manager, where our scf.input file is in the running condition. So it will take a little bit time to simulate this structure. So in the meantime, we can go for the analysis, like whatever the property you want to analysis from this structure, then you can go to the analysis. You can select the simulator, RESCU, and you can see this is the analysis. So these are the analysis parameter that you can study based on the density function theory method from this RESCU software. So like we have the density of state, band structure, Malkin population, and potential. And if we talk about the material property based on this nanodical software, so you can see this is the nanodical and this is the analysis. So these are the various analysis parameter. So based on the density function theory, with the help of nanodical, you can analyze all these parameter for any material, like density of state, effective potential, total energy, band structure, charge, Hessian matrix, Phonon band structure, electron density, potential, transmission channel, eigenstate, full band structure, effective mass, complex band structure, ZT, that basically for the thermoelectric application, Phonon full band structure, Phonon density of state, Phonon transmission channel, and modulus. So these analysis parameter you can study from the nanodical. And if we talk about the RESCU, you can see this is the analysis. So any simulator you can select, like this is the density of state that has been selected. And here you can see K point sampling, energy range, number of energy point, and this is the sampling method. Like we have the Fermi direct, Gauss, tetrahedral, so various methods are there. So as per your need, you can select. Also, you can define the simmering sigma. You can see this is the projected density of state, and this is the local density of state. So any density of state you can study. And you can see this is the band structure. So this is the symmetry K point. And if we talk about the Berlin path, so you can see this is the Berlin path for this WSE2 material. You can also change the symmetry K point from this add option. You can see this new symmetry point has been added. Also, you can change their value. And if you want to delete anyone, you can click cancel. And then you can select preview and then you can apply. So this is the band structure. If we talk about the density of state, here you can define some key point sampling so that you can get the plot. Here you can see I have taken a default parameter n1, n2, n3 is equal to 3. So once you select the parameter, you can select this generate file so that their input file will be generated. Here you can see our scf.input file has been completed. So in this similar way, you need to run the analysis input file. This is the band structure that we need to run. And this is the density of state input file. So in the queue condition, you can run multiple input file. So once this input file will be completed, then this input file will start automatically. So multiple input file you can run in the queue condition. And if you want to show the stepwise step procedure, you can see this is the RESCU log output folder. You need to select, right click, select this open with. Here you can see this is the RESCU software. This is the basic information, like this is the location. This is the pseudo potential database. Here you can see step by step procedure. Like you can see total energy, pro matrix, so this is the differential of energy, delta T, and this is the time. You can see this is the band structure simulation. And now this band structure is running. So in this scf.input file, I have defined the DFT method. Here you can see we have the various builder, like you can create any device structure. You can convert any structure into device. You can also create an interface. You can create any crystal structure. You can create any surface slab structure. You can also create the symmetry structure, graphene nano ribbon structure, nanotube, grain boundary, nanotube, nanowire structure, disorder graphene-like structure, disorder zinc blend-like structure, icosahedron, cuboctahedron. So these are the various builder that will help you to build your desired structure. Suppose if you want to create a graphene sheet, you can select this disorder graphene-like structure. Here you can see at site A, we have the carbon element. At site B, we have the carbon element. And here you can see this is the bond length and this is the supercell. So once you define all these parameters, select this preview so that you can easily create a graphene sheet. You can see this is the graphene sheet. If you want to change the supercell, so if you want to change the length of the supercell, here you can change. Select this preview. So in a very quick time, you can create the graphene sheet from this disorder graphene-like structure. So this is the graphene sheet. If you want to create a boron nitride sheet, any sheet, then you need to replace the element. Suppose if you want to create a boron nitride, then we need to replace all this carbon element from the site A to boron. You can see we need to replace all the carbon with the boron, and from site B we need to replace all this carbon with the nitrogen. Then it will create a boron nitride sheet. You can see these are the boron, these are the nitrogen. Select this preview. You can see this is the boron nitride sheet. And then you can select this build option. And if we talk about this disorder zinc blend-like structure, you need to define the information, bond length, supercell, and then select this preview. So you can see this is the disorder zinc blend-like structure. If we talk about the surface structure, you can see if you want to create a surface slab, so for cleaving the plane, we have this Miller indices like SKL value. You need to select whatever the combination you want, like 100, 101, 111. So whatever the combination you want, you need to define. Go to the slab option. So if you want to include this slab, you need to enable, and then you can vary the thickness and the vacuum. So first I would like to import some material from our existing database. Like you can see, I would like to import some semiconductor. Like you can see, this is the silicon semiconductor. If you want to show the face center cubic structure, body center cubic structure, then we have this redefined crystal. Here you can see, this is the redefined crystal. By expressing the new cell vector UVW as a linear combination of ABC. Here you can see we have the face center cubic structure and we have the body center cubic structure. Like you can see, this is the FCC. So this is the face center cubic structure of the silicon semiconductor. You can also select the body center. So as per your needs, you can select the structure, select this preview, go to the build option. And if you want to create a surface slab, you can see all the options are enabled, like grain boundary, nanotube, nanowire. So if you want to create a surface slab, you can see you can define the Miller indices value, then go to the slab option. You can also vary the thickness and the vacuum energy. If you want to increase the thickness, if you want to increase the vacuum, so you can see this is the surface slab of the silicon face center cubic structure. So in that way, you can create the surface. And if we talk about this grain boundary, you can see here you can define the sigma value. So any sigma value you can define. You can define the axis theta and cos theta. You can also define the grain boundary plane EH scale value. So any combination you can select, and then you can go to this preview. Now you can see this is the grain boundary plane for the silicon semiconductor. And if you want to create a silicon nanowire, you need to select this nanowire, and here you can define the wire direction. Like this is the 100, 110, 111. And here you can define the cluster parameter, like cluster radius, surface energy for the 100, 110, and 111. You can see this y direction has been selected. Select this preview. So you can see this is the silicon nanowire in the direction of 100. So any direction you can select and select this field option. You can see this nano ribbon is quite thin. So if you want to increase the length of this nanowire, you can select this field option, select this redefine crystal. And in any direction, you can increase the length, either A direction, B direction, and C direction. So here you can see, I would like to increase in the transport direction, that is C. Select this preview. Now you can see the length of this nanowire has been increased. Here you can see our band structure and density of state has been completed. So if you want to show the graph, first you need to select any file, right click, select this open containing folder. You can see this is the location of our file. These are the input file, and here you can see we have the result. You can see this is the band structure output file in the text format. This is the real space density, this is the density of state, and these are the potential. Also you can see the mat file has been generated. So if you want to get the plot, you can go to the device studio, select our input file, select this simulator, you can select this RESCU, go to the analysis plot. So once you click on this analysis plot, then you need to choose the location of your file. So the location of project file you need to select. You can see this is my project. This is my WSE2 folder. This is the RESCU crystal folder. This is the result folder. And here you can see band structure, real space density, density of state. These are the potential. So this text file we need to select. Here you can see this band structure has been selected, and you can select this open so that you can get the plot of the band structure. You can see this is the band structure plot for the WSE2. You can see this is the energy range, and here we have the symmetry K point, G, M, K, and G. So as you know, in the input file, I have defined the collinear spin so that we can get the plot for the spin up and spin down. You can see this is the spin type, spin up, spin down, and this is the both. Here you can see this is the spin up band structure. This is the spin down band structure. And here you can see this is the spin up and spin down. So both the value are overlapping. So this is the band structure plots. And if you want to show their band gap value, so here you can see we have the mat file. So this is the WSE2 band structure mat file. And this mat file you can import either origin or MATLAB to get the band gap value. You can also use the MATLAB online, like you can see. So if you want to use MATLAB online, so just you need to create an account on the MathWork. So on this website, you just need to create an account and you can use, you can see, this is the Open MATLAB online that is for free. So you need to select this Open MATLAB. And if you have the download version of the MATLAB, you can also open. You can see this is the MATLAB. You can go to your project location. Here you can see this is my WSE2 mat file. You need to select and you can import here. Here you can see the WSE2 band structure mat file has been imported. And you can double click, then you will get the output. You can see this is the so you can see this is the band gap value 0 because we have taken the default parameter. So whenever you define the accurate parameter, then you will get the exact result. So here just I am showing you the example, then how you can define the parameter and how you can generate the input file and how to do the simulation. So once you define the accurate parameter, then you will get the accurate result. You can see this is the energy. You can see this is the Fermi energy. And these value are in the Hartree. You can see this is the Fermi energy in the Hartree. So this is the band structure. And if we talk about the density of a state, so in the similar way, you can select rescue analysis plot. This time you can select this density of state and select this open. Now you can see this is our density of state. with respect to energy in the unit of electron volt. So this is for the spin up. Also, you can select the spin down. You can also select spin up and spin down. So here you can see both the value are overlapping. And if we talk about the DFPT, like you can see, this is our silicon. So if you want to add the DFPT method, like you can see, this is the RESCU, this is the DFPT. So from this DFPT method, first you can see this is the basic setting, and here you can see this is the task. So with the help of this DFPT, we can calculate the Phonon band structure, Phonon density of state, Phonon band structure and Phonon density of state in a single click, optical property calculation and Raman property calculation. So all this calculation you can study with the help of DFPT. Here you can see, if you want to calculate the optical properties, basic setting, and here you can see this is the optic parameter, like damping factor, electric field direction. So if you want to select the Raman properties, so these are the basic setting, and you can see this is the Raman parameter, like damping factor, key point, Cartesian, income photon polarization, outcome photon polarization, income photon wavelength, and the temperature. So you can define your own parameter. You can see, you can define the simmering sigma. You can also define the resolution. This is the SCF method. This is the exchange correlation function. You can see this is the iteration control. This is the SCF parameter. And here you can see this is the DFPT parameter. You can see this is the DFPT method. We have the Sternheimer, and this is the Chebyshev filtering. So any method you can select, then go to the basic setting, spin type, and Raman properties. So once you define all the parameter, you can click on this generate file. Now you can see, once you click on the generate file, then it will generate 4 input file. First is scf.input file, dielectric.input file, phonon.input file, and Raman.input file. So you need to run all this analysis input file from the top to bottom. Like first you need to run the scf.input file. Then you need to run the dielectric input file, because this dielectric input file will take the output from the scf.input file. Similarly, you need to run the Phonon input file. Then you need to run the Raman.input file. Now you can see it is getting finished of the scf.input file. And now this dielectric.input file is in the running condition. So it will take a little bit time to simulate this structure. And once this structure will be simulated, a MAT file will be generated. A MAT output file will be generated. You can see the dielectric input file has been completed. And now this Phonon.input file is in the running condition. So you can see this is the toolbar. So if you want to measure the distance, if you want to measure the angle, if you want to measure the dihedral angle, and if you want to measure the vector value, So here you can see, this is the distance measurement, angle measurement, dihedral angle measurement, vector measurement. So for the distance measurement, first we need to select this one. Select any two atom. You can see this is the distance between these two atoms, 3.840 angstrom. Here you can see our input file has been completed. So once the input file completed, you can select any file from this RESCU DFPT. Select this open containing folder. You can see these are the input file, and here you can see this is the result file. So you can see the SI dielectric.mat file has been generated. SI dielectric auxiliary wavelength has been generated. And here you can see SI Raman.mat file has been generated. So if you want to get the plot, you can open this device studio, select this silicon, select the Raman.input file. You can right click, select this open with. And here we need to write some script to plot the graph. Here you can type RESCU, and then you can select the location. Here you can see this is the location of my output file. Here you can paste, and here you can type .mat. So this script I have written for the Raman plot of the silicon structure. Once you write this script, you need to select this save option so that this script will be saved. And once this script will be saved, again you need to run this input file. So in a very quick time, it will get finished. So you can see this is the running condition. And now the file has been completed and their graph has been generated. If you select the location of the graph, you can see this is the result. And here you can see we have the silicon Raman plot for the polarized silicon Raman plot for the averaged graph. So if you want to show the graph, you can import this file into MATLAB. You can see I have selected this file. You can go to the MATLAB, and here you can import. Now you can see the file has been imported. You can see this is the SI Raman plot for the averaged. You can double click, then you will find the graph. You can see this is the Raman polarized graph with respect to Raman shift. So you can see this is the Raman shift and this is the Raman intensity. In the same way, you can select this output file and you can import into MATLAB. Again, you can double click, then you will find the Raman averaged polarized graph. And if you have installed version of the MATLAB, from this browse option, you can select the project location. And then you can select this folder. Now you can see the file has been imported. This is our silicon input and output file. And here you can see this is the Raman polarized graph. And this is the Raman averaged polarized graph. So this is the Raman graph with respect to Raman shift and Raman intensities. So this Raman I have calculated from the DFPT method. So in the same way, if you want to define the DFT method, you can select simulator, RESCU, and you can select the CSCF calculation. And then you can go to the analysis file. And if you want to define the DFPT, you can select this RESCU, select this DFPT. And all this calculation you can study from the DFPT method. So the procedure is same. Just you can select the task, define the parameter, click on generate file. Here you can see SCF.input file, dielectric.input file, Phonon.input file, and Phonon density of state.input file has been generated. So similarly, you need to run the SCF input file first, then dielectric.input file, then Phonon.input file, then you can run the Phonon density of state.input file. So I have shown you the how you can generate the input file with the help of RESCU. You can define DFT parameter and you can define DFPT parameter. So any material, any crystal, any molecule, you can study from this RESCU software. And if you want to study this nanodical, so this nanodical tomorrow I will cover. So if you have any query regarding the RESCU software, either with the help of density function theory, either with respect to density function perturbation theory, so you can ask. So if anyone has any queries, you can unmute your mic. Either you can drop the message in the chat box so that I will ready to help you.
Hello, sir.
Yes, sir.
My question is how to calculate the Gibbs free energy.
Which one, sir?
Gibbs free energy.
Gibbs free energy.
Yeah.
So if you want to study the energy,
Hmm.
so tomorrow I will cover this nanodical, and in the nanodical we have the energy. So in that
Okay.
total energy, you can get the kinetic energy, refractive energy, Gibbs energy. So all these parameter you can get from this total energy. So
Okay.
that I will cover tomorrow.
The second question is, sir, how to adsorb our OH radicals on any plane or any HKL plane?
Which was, sir? Can you repeat?
How to adsorb the OH radicals on HKL plane?
XOD
Hello.
plot, sir.
Hello.
Yes, sir. XOD plot you are talking.
No. For example, we make some 110 plane surface.
Okay.
We have to adsorb the OH radicals on that plane.
So you can see this is the surface,
Ah,
and here you can define the plane HKL value.
okay.
So any combination you can select, either 1, 0, 0. If you want
Okay.
to add
For example, we built up the plane HKL 101 plane, and we have to adsorb the OH radicals on that plane.
Sir, can you write your message in the chat box? As I am not getting your point.
Sir,
Yes, ma'am.
so my doubt is this: as you were drawing like a toluene or something like that, there's a repulsion and interaction between the molecules. This will plot like in a general, or this will consider that attraction, repulsion, and everything. That bond angle will, bond length, everything will be changed.
No, ma'am. It's up to you. If you want to change, you can.
No. As
And
we are just drawing that, so it will inbuilt in this software, or we have to uh, like give like specific attention on that.
no, just you need to select the structure. This software will automatically create.
Okay.
And also, if you want to go to the theory parts, so here you can see this is our official website, nanoacademy.com.
Okay, sir.
You can go to the bottom of the page. You can see this is the document and tutorial. So you can see these are our product, Nanodical Plus, Rescue Plus, and this is the QT for the quantum technology. So you can select your product, then you will get the theory and tutorial.
Okay, fine, sir.
And also you can get like what parameter you can define. So you can see these are the function. You can see all the theory are mentioned. So whenever you get the time, you can visit our website, so that I hope you will get more familiar about the software.
Okay, fine,
And
sir.
if you want to show the publication paper of this rescue and nanodical, and the publication paper, you can select this technical insight. And here you can see, you can select the product like QT, nanodical, and rescue. You can see this rescue, and these are the various publication paper.
तो मैं तुम्हें बता दूंगा फिर कैसे लिखना, ठीक है? इसमें होंगे 10 पेपर, इसमें 17।
These are the rescue publication paper. Also, you can search on Google Scholar page. So you can visit the Google Scholar page, and just here you can type rescue. See, these are the various publication papers in various domain with the help of rescue software.
अरे मैं इससे करूंगा तो कुछ मेरी तरफ से भी होना चाहिए ना कंट्रीब्यूशन.
Yeah, excuse me, sir.
इसमें नहीं होता.
Deepak sir, can you hear me?
Yes, ma'am. Yes, ma'am.
बता दूंगा मैं.
Good afternoon, sir. I just wanted to know how to decide the size of a supercell we talked about.
तो अक्टूबर में खत्म.
So, ma'am, it's up to you, like how many nanometer you want to design.
Okay.
If you want to define the supercell structure,
Yeah. Okay. And the other thing that I wanted to know was when you said no in the beginning that the normal laptop cannot be used for this. So is there a way that we can optimize the runtime? Or
ma'am,
how
you can
much
see
time will
this
it
is my
take to run
normal
on a
computer.
laptop?
Ma'am, you can
Yeah.
see this is my normal computer that I am
Yeah.
simulating.
Yeah.
But when you increase the number of atom, then your simulation time will be increased.
Yes, that's true. So how can we optimize that runtime on our normal laptop or desktops?
Okay, so if you want to optimize the structure, you can select this relax option.
Mm-hmm.
Here you can select the method. So any method you can select and generate their input file.
Okay.
You can see this relax input file has been generated, and once you run this input file, then it will generate a output file. So optimize
Okay.
output file will be generated.
Okay. Thank you, sir. There is one more thing. How to get GIF files for the results? Means these files that we are getting as outputs in the results. You said we can do it in the MATLAB, but is there a possibility that we can get the GIF files, CIF files?
Okay. So if you want to get the CIF file, so you can browse. Like if you want to take a SiO2 CIF file, you can see this is the SiO2,
Yeah.
and you can download this CIF file. You can see this is the CIF file, either computed, conventional, primitive cell, any structure you can download. You can see the file has been downloaded, and this file you can easily import in our device studio. So you can select this file, select import local, and then you can select the location of your file. You can see this is the file.
Yeah. Yeah, but this is for the input. For the results that I have got, for the graph that I need to plot or the analysis that I have today, for that I'm asking, is it possible to get the CIF files for the
Yes, ma'am.
results?
Yes, ma'am. Like you can see this is the CIF file that I have
Yeah.
imported, and if you
Yeah.
want to calculate their analysis parameter, so you
Yeah.
can select simulator, RESCU. You can define any method like DFT method, DFPT method.
Mhm.
You can see you can define your
Yeah.
own parameter. Click on generate file.
Yes.
Now the
Great.
input file has been generated, and then you
Yes.
can run this input file, and then you can go to the analysis part. So any analysis you can select, and once you do the simulation, then it will
Yeah.
generate a output file.
Yeah.
And I have already shown you how
Yeah.
to take the data. Like you can see, this is the once. This is the rescue crystal. I have simulated band structure and density of the state. So if you want to plot the graph, select simulator, rescue, go to the analysis plot.
Yes.
Select your project location, go to the result folder. You can select the file, select this open. Then you can visualize the data.
Yeah, that's right. Okay, thank you so much.
Hello, sir.
Yes, sir.
How to make the composite, professor?
How to make a?
Composite. For example, I have to make composite of graphene and metal oxide.
Okay. So if you want to create a composite of graphene and nickel oxides, then you can select this file, select this new option, select this crystal builder.
Mhm.
So if you want to design a composite structure, then you should know their space group. Then their Bravest lattice will automatically selected. You can define their ABC value. Here you can select the element. So graphene, nickel oxide, you can select. You can define their fractional coordinate point P1, P2, P3, and then you can design the structure. So all this information you should know so that you can create the composite.
Okay.
Excuse me, sir.
Yes, ma'am.
Yeah, can you hear me? Yeah. So, like, if you wanted to do simulation on optoelectronics, thin films, do you give any
Yes,
courses?
ma'am. Up to electronics application you can also study. So
Okay.
based on the atomic method you can study, not for the like layer wise. So
Okay.
atomic simulation you can study from the rescue and nanodical. You can
Okay.
any material like optoelectronics, thin film, any
Oh.
structure you can create.
So, what do you calculate from thin films? Like, what is the
Like you can see, ma'am. 1 second. These are the analysis parameter for any material you can create.
okay?
And for the device, like if you create any device structure, 1 second. I can convert this structure into device.
Okay.
And you can see these are the device properties like
Okay.
density of state, effective potential, total energy, scattering state, transmission spectrum, photocurrent, IV curve, charge, electron density, potential, conductance, thermoelectric current, and Seebeck coefficient. So for
Okay.
any device structure, this parameter you can study.
Okay. So for thin films, all right.
Yes, ma'am.
Oh, yeah. Thank you.
Hello, sir.
Yes, sir.
Hello, sir.
Yes, sir.
Yeah.
Yes, sir. Tell me.
If I want to, yeah. If I want to study an adsorption of gas molecule on the surface of metal oxides, will it be possible by using this?
Yes, sir. Yes, sir. It is possible. So just you can create your structure. You can
How I
create
can
a
do that?
surface of metal oxide. So, sir, first you need to import that material. So that metal oxide you can import. Either you can create your own structure from this crystal builder. Either you can import the material from this import local option. Like you can see metal oxide. So any metal oxide you can select. You can create a supercell first. Then you can add a gas molecule. So if you want to add any molecule in this structure, like here I am taking this benzene molecule, you can select the benzene molecule. You can control C. You can select this structure. You can control V. And this structure, you can move from this move option. So any position you can move. Also, you can change their angle from this rotate item option. So that is a
Okay, sir.
possible.
Okay. Okay.
Hello, sir. Hello.
Thank you, sir.
Yes, sir.
Sir, you show me the this structure now. Then how to optimize that gas molecule and that crystal structure together?
So, sir, the process are same for any structure. Like if you want to optimize this gas molecule and this structure, the process are same. Select this in rescue, select this relax, define your method. Any method you can select and generate their input file.
And that final
You need to
optimized
run this
structure.
input file, then it will generate a yes.
After optimization, we have to use the same optimized file for further calculation.
So, sir, once this input file will be optimized, then it will generate a output of optimization.
Okay.
So that output you can import and then you can study their properties.
Okay.
This property you can study with the help of DFT.
Hello, sir. Can we generate a few layer of 2D materials?
Yes, sir. You can also create the layer of 2D material. Like first, I can import some MOS2. One second. Like you can see, this is the WSA2 2D material. So we can create a supercell of this structure. You can see this is our single layer. You can copy. Either you can go to this mirror option and here you can define the normal vector. So all this application I will cover tomorrow for the device. So just here you can define the normal vector x, y, x, z, y, z. So at any position you can create the layer. Either 2 layer, 3 layer, 4 layer. So multiple layer structure you can design.
Okay, sir. Thank you so much.
Hello, sir.
Yes, ma'am.
So can we draw a heterostructure system, a layered system of two different materials?
Yes, ma'am. You can draw. Like if you want to define a heterostructure, so we have this interface builder. So here you can define the different material in the structure A and structure B. Like here you can see, if you want to define some Like you can see, this is the silver. Again, I would like to import some gold. You can create the supercell first, and then you can go to this interface builder. So here I am taking a simple structure, interface builder. Here you can import your material. Then select this match. You can select this preview. You can see this is the heterostructure of the silver and gold.
Okay, sir. Thank you.
So this question I need to check, and then I will let you know. So I think there is no question. So we will meet you at 2 p.m. so that you can get the hands-on practice. Sir, here you can't create any MATLAB input file. Here you can create an input file, that is scf.input. So basically it will generate a MATLAB output file, not the MATLAB input file. So Sevier coefficient is basically for the device application. So device application I will cover tomorrow. And also I can show tomorrow the thermoelectric parameter. So once the result, you will get the mat file. Here you can see, these are the mat file. Like you can see, this is the SI Phonon.mat file. This is the SI Raman.mat file. You can double click, then you will get the data. And if you want to plot the graph, so here you can see I have written the command. This command I have written for the Raman. So similarly for the optical Phonon value structure, Phonon density of state, you can write and then you can get the plot. So procedure are same for any band structure, for any structure, either mixed metal oxide, semiconductor, complex structure, alloy, any structure you can create. And for analysis of the band structure, first you need to generate the scf.input file, then you can go to the analysis. Here you can select the band structure, you can define the parameter, generate the input file. So once the input file will be generated, so first you need to run the scf.input file, then you can run the band structure.input file so that you can get the band structure plot. So the procedure are same for any structure, any material. Now I am going to stop this session and we will meet you at 2 p.m. So if anyone has any query, that time ask. So that time I will try to help. You can open your C drive. So you can open this C drive. select this Device Studio folder. Again, you can select this Win folder. Then you can drag and drop, and then you will find this Device Studio application file. So this file you need to open. So you can double click on the file. And then you will find this interface. So you can select this create a new project. You can select this OK. And here you can enter the project name. So participant kindly open their software. And you can write the project name. Then you can select the location where you want to save this project. Then you can select this save option so that your project will be saved. So during this session, you need to follow the same procedure that I will show you. Because once you increase the number of atoms, then your simulation time will increase. And here we have the timing at 4 p.m. So just I am taking a default simple structure so that we can get the output easily. So I hope everyone has been open their software and they also has created a project file. You can see this is my project name. So basically, first I will show you how to define some DFT parameter and you can analyze their various properties. And after DFT, I will also show you how you can define some DFPT parameter and how you can calculate their analysis, like Raman parameter, optical parameter, density of state, Phonon density of state. So first, we need to import some material. So if you want to import any material, you can click on this file. You can select this import button. Then you can select this import local. So if you want to import any material from existing database, so you need to select this file, click on this import button. Then you can select this import local. Then you will find the material database. So you can see this is our material database. Like you can see this is our C drive, Device Studio folder, and this is the material folder. So in the first session, I have already shown you, like we have a very complete list of material database like 0D material, 1D material, 2D material, 3D material, and organic material. So I would like to import some 3D material. So you can select this 3D material. You can select this conductor. Again, you can select this pure metal. And here I would like to take nickel. You can see this is the nickel. So this is the nickel pure metals. So you can select this material. Then you can click on this open. Then this nickel material will be imported in our device studio. So you can take this nickel, select this open. Now you can see this is our simple nickel structure.
Excuse me, sir. Sir, how did you rotate the structure? I'm not able to rotate it.
You can see this is the rotate option. You can select, and by using the right button of the mouse, you can rotate like that. You can press
Yeah,
the
thank you
right.
so much.
Yes, you can press the right button of the mouse, and then you can rotate like that. So this is our simple nickel structure. Here you can see this is the property of this material. This is the vector value, vector A, vector B, vector C, and here we have single atom. And you can see this is the total area of this lattice. Here I have taken a simple example so that we can get the output in a very quick time. So after this session, you can take your own structure. You can also increase the number of atom, and then you can do the analysis. Yes, the process are same for simulating any simple structure or complex structure. So once you imported the material, and if you want to simulate the material, you can select this simulator. Here you can select this rescue. So for simulating any material, first we need to select the simulator, select the rescue, and first I would like to define the DFT parameter. So if you want to define some DFT parameter, then you need to select this self-consistent field calculation. So this self-consistent field calculation you can select. And here you can define the parameter. So any parameter you can take, like you can see, this is the simmering sigma in the unit of electron volt. This is the resolution. If you want to change, like you can enter the value. Like you can see 0.3 resolution, go to the method. You can select this linear combination of atomic orbital. So this method I would like to select. So these are the basic setting that user need to define. Like we need to define the symmetric sigma. We need to define the resolution. We need to define the method of the DFT. Like here you can see this is the real space and this is the linear combination of atomic orbital. So you can take this linear combination of atomic orbital. Then you need to define some k-point sampling. Like as an example, I have taken 9 for the N1, 9 for the N2, and the 9 for the N3. And if you want to know the theory for this k-point sampling, so you can visit this website. You can visit this nanoacademy.com. Go to the tutorial. Need to select this rescue. Select this getting started. You can see this is the pseudo potential theory. This is the numerical atomic orbital, the element, the pseudo potential database, geometry, simulation parameter, input syntax, calculation type. So every parameter you can get from this website. So you can see this is the symmetric sigma 0.01. This is the resolution 0.3. This is the method linear combination of atomic orbital. This is our exchange correlation function. And this is the k-point sampling. N1, N2, N3 is equal to 9. So once you define this parameter, then you can move to the iteration control. You can see these are the iteration control parameter. Then you can select this basis set. Here you can see this is our nickel atom and their pseudo potential file, double zeta polarized. Also you can see this is the atomic database and you can see this is the user defined. So if you want to import your own pseudo potential database, you can select this user defined. You can see this is my device studio and here you can see we have the pseudo potential database. Like this is the neutral atom database which is called pseudo potential, and here we have the general or the specific atom, and this is the virtual crystal approximation. Any folder you can select, like you can see this is the general pseudo potential database. Also you can see this is for a specific element.
Sir, can you repeat for 1 minute what you said just 10 seconds before?
Okay, very good, sir. Like here you can see This is our nickel atom and their pseudo potential database file, double zeta polarized. So if you want to include your own parameter, own pseudo potential file, you need to select this user defined. You can see this is my C drive. This is my device studio. Here you can see this is the neutral atom database. In the neutral atom database, we have the general database of pseudo potential, and we have the specific element and their pseudo potential database. Also, you can see this is the virtual crystal approximation. That is basically for the doping. So any folder you can select, and then you will find the pseudo potential database. Like you can see, this is the silver LDA double zeta polarized .NAD file. Also, you can see this is the single zeta polarized. Here you can see this is for a specific element. You can see this is the nickel, this is the LDA, and this is the PBE. You can see nickel bulk phase center cubic structure, nickel double zeta polarized .NAD file. Also, you can see this is the PBE. So this is the existing database of the pseudo potential. If you have your own parameter, own file, you can just locate the file, select this open. Here you can see this support .NAD file and .mat file. So this is the basis set. And here you can see this is the Spintronics application. So if you want to include the Spintronics application in your material, like you can see, this is the default noise spin, this is the collinear spin, and this is the general spin. So you can take this collinear spin. You can see the collinear spin has been included, and here you can see this is our nickel and their collinear spin maximum value. You can also change as per your need. If you want to change the value, you can double click and you can change like that. So you can see this is our Spintronics application, collinear spin. Also, we have defined the maximum value 2. So once you define all these parameter, you can click on this generate file. So once you define all these parameter, like this basic setting, symmetric sigma, resolution, method, you can select linear combination of atomic orbital, exchange correlation function. Here you can define some k-point sampling, n1, n2, n3 is equal to 9. Then you can see this is the iteration control. This is the basis set. And this is the Spintronics application. So once you define all these parameter, you can select this generate file, so that their input file, scf.input file, and atom.xyz file will be generated. You can press this generate file. You will find this nickel folder. You can click on this arrow. Then you will get the rescue crystal folder. Again, you can click on this arrow. Then you will find the input file. Like you can see, this is the scf.input file, and this is the atom.xyz file. In this folder, we will get the DFT input file, and in this atom.xyz, we will get the atom and their Cartesian coordinate point. So if you want to show the script, you can select this scf.input file. You can right click, then you can select this open with. Now you can see these are the parameters that we have defined. So the graphical user interface, we have defined this parameter. So basically this is the script that this software will automatically generate. So there is no need to write any script for any structure. Just you can define your parameter and click on generate file. You can select this atom.xyz file. You can right click, select this open with. Here you can see we have the single nickel atoms. These are the coordinate point. And here you can see we have the collinear spin magma value. So I hope everyone has been generated their scf.input file and atom.xyz file. So once you generate the input file, then we need to run the scf.input file. So if you want to run this input file, right click, select this run option. So as you know, we have given you the evaluation license. So only single core you can utilize. But this software also has the capability to run the job on the parallel core, like suppose 5 core, 10 core, 15 core. So there is no limitation of core. You can define up to 128 core. Again, you can select this run option to run this job. You can select this run option to run this job. Now you can minimize this interface. Here you can see this is the job manager where the scf.input file is in the running condition. So I hope everyone has been run their input file and the input file is in the running condition. So this is the procedure for defining the DFT parameter and generating their input file. So this similar procedure you can define for any structure. Either it could be simple structure, complex structure, molecule, crystal, or any structure. You can select the same procedure. First, you need to import the material, select simulator, go to the rescue, select your SCF calculation, and you can define the parameter. So based on your research, you can select the parameter and click on generate file. So once you click on generate file, then the scf.input file and atom.xyz file will be generated. And for running any input file, we need to select that file, right click, we need to select the run option. Again, we can select this run option to run this job so that your input file will be run. So after running this input file, in the meantime, you can go for the analysis. Like what the properties you want to analysis for this structure. You can select this simulator, select rescue, select this analysis. So if you want to analysis this parameter from this material, we can select the simulator. We need to select this rescue. We need to select this analysis. You can see these are the analysis parameter then that we can study from the DFPT density function theory with the help of RESCU software. So with DFT, we need to select any input file. You can see this is the density of state. So if you want to select any analysis parameter, you can double click on that file. Then the density of state will be selected. You can see density of state has been selected, and this is the density of state parameter. You can see this is the K-point sampling, energy range, number of energy point, K-point sampling method. This is the simmering sigma. So if you want to change any parameter, like if you want to define some K-point sampling, then you can enter that value in the N1. You can see this is for N2 and this is for N3. So N1, N2, N3 is equal to 15. So this K-point sampling you can include. And if you want to change the energy range, you can see we will get the plot of density of state in this energy range from minus 10 electron volt to 10 electron volt. So if you want to change this value, you can remove this value. And here you can enter the energy range. You can see -5 electron volt, comma 5 electron volt, so that we can get the energy plot for this density of state from -5 to 5 electron volt. You can see this is the number of energy point. You can see this is the K point sampling method. Like this is the Fermi direct. You can select this Gauss method. So this Gauss method you can select. And similarly, if you want to change this simmering sigma, like you can see this is the 0.01 electron volt. So if you want to change this value, like if you want to enter 0.1, then you can enter that value. So here you can see I have taken this density of state. This is the K point sampling. N1, N2, N3 is equal to 15. This is the energy range from -5 electron volt to 5 electron volt. Number of energy point, K point sampling method, that is Gauss. And here you can see this is the simmering sigma, that is 0.1 electron volt. So once you define all these parameters, then you can select this band structure. So you can double click on the band structure, then it will be selected. Here you can see band structure has been selected. Again you can double click, then you will find their parameter. You can see this is the density of state parameter. Double click, and here you can see this is the band structure parameter. So you can see this is the symmetry K point, and this is the Brillouin zone path. You can see this is our K point sampling method. So this is our symmetry K point. Like you can see, there are various K point. If you want to delete or if you want to add any more K point, then you can select this add option to add a new K point. If you want to delete, you can select any K point and click on this delete option.
Hello, sir. How can you rotate the brilliant zone?
So you can press the right button of the mouse and then you can rotate. So for rotating any structure or any Brillouin zone path, you can press the right button of the mouse and then you can rotate like that.
I'm doing the same, but it is not happening in my case.
On the top, that's rotate button that you have to click.
No, ma'am, no need to select that button. You can see the arrow button has been selected. In this dashboard, you can press the right button of the mouse and you can rotate.
Okay.
So this is our Brilliant Zone path. So you can see I have selected density of state and band structure. So once your parameter will be selected, you can define your parameter, then click on generate file. Then the input file of the density of state and band structure will be generated. Here you can click on this generate file, and you can see the density of state dot input file and band structure dot input file has been generated. Here you can see our SCF dot input file has been completed. So in the same way, we need to run the analysis input file. You can see this is the density of state. You can select this file, right click, select this run button, and here you can press this run to run this job. Now you can see, you can minimize this interface, and here the density of state dot input file is in the running condition. So in the meantime, you can also run this band structure dot input file in the queue condition. You can see this is the queue condition. Here you can see the density of state has been simulated. Also, the band structure has been simulated. So once your simulation will be completed, you can select any file. Like you can see, this is the rescue log.output file. You can select this open containing folder. You can see this is my project location. You can see these are the input file, scf.input file, density of state.input file, band structure.input file. This is the atom.xyz file. Here you can see this is the result file. You can see we have the band structure output file in the text format. This is the real space density, and this is the density of state output file. So once your simulation completed, you can select any file, then you will find the location of the project. Also, you will get the result folder. So I hope everyone has been run their input file and their input file has been completed. So once your input file completed, then you will get the output file, and that output file you can visualize from this simulator. So if you want to visualize the output of this RESCU, like density of state and band structure,
I'm not getting the actually things that I'm encountering with one error that is called in the density of state the page is invalid input. Please input should be the legal content.
sir,
So,
can you send the screenshot of that error?
yeah, should I share my screen?
No, sir, you can share that in the WhatsApp group so that I will check.
Okay.
So, sir, did you follow the same procedure?
Yeah, I follow the same procedure. Maybe some minor mistake is there. So you can see now. Okay. In the density of state page, input is invalid, something like that. It is saying.
Sir, I think there is some parameter mismatching.
Yeah, something like that. So can you just so maybe energy range? I put an energy range in such a way that -10, comma space 10. That is
No,
okay.
sir, no need to enter the space.
No
Just
need to enter
-10. Yes, -10, comma 10.
10. Okay. Then projected file something is there. To click on the projected file, no, nothing. Empty band.
No need to click anywhere. So just select the generate file.
Yeah, maybe that minor mistake was there. So what is my suggestion to you now? My request actually. I'm not from this simulation background.
Okay.
I'm from agri-tech background, and I have some other problem. That's why I enroll in this simulation work. So please, before now you are explaining this problem now, please, for the sake of me, please explain what is the density of state, what you are exactly the case sampling and all these things, so I can understand in better way. Right now I'm just clicking like a robot, whatever you are saying, that thing I'm following very briefly, not in detail. Later on I can go in details and everything, whatever the things are required for me. But presently, if you'll explain briefly what is this nickel structure and what exactly you are doing with density of state and all these things, so it will be better for me to understand, and I can be in a I can learn something from this
So
work.
then it will take more time to explain.
Very briefly, mean very shortly. Maybe I have learned little bit physics during my if possible not, then it's fine. But right now my situation is like that actually. I don't know. Rest of the guys are expert. Seems to be expert in this field.
Yes, because here you can see, sir, you can visit this website nanoacademy.com, and then you will find the document and tutorial.
Yeah, I will definitely go through that. No issue in that. But right now, maybe a very layman language you can tell what exactly you are doing. If I will get that glimpse also, that will be fine for me.
Okay, sir. So like here you can see, this is the parameter for calculating band structure. Also, you can see the theory are mentioned, like what parameter you need to select. You can see every step by step procedure are mentioned.
Okay. So
just you can go throughout this.
Yeah, definitely I will go through that. No issue. But okay, fine. You can continue. What in your space you can continue. No problem. I will just follow. Yeah.
Okay, sir.
Hello, sir.
Yes, sir.
My program is finished. I got the result for band structure and density of state, but I have to use the same in origin. Which data I have to extract for origin?
So the mat data you can export in the origin. Here you can see. This is the result folder.
Yes, I got it.
Either you can import this band structure text file in the origin, either you can also import this band structure mat file.
I tried to open in origin, but I didn't open.
Because I think origin support this text file. So this band structure text file you can import.
Okay, just I.
Because
Okay.
here I don't have any origins software.
Yes, I
So
have.
I have MATLAB.
It work.
Okay. Nice.
Okay, thank you.
So once you completed this input file, so if you want to show the graph, you can select the simulator, RESCU, select this analysis plot. Then choose the project location. You can see this is my project location. You can open this folder. Again, you can see this is the nickel folder. Again, you can see this is the RESCU crystal folder. This is the result folder. And here you can see these are the result that we have simulated. So this is the band structure output file. This is the real space density. And this is the density of state. Also, you can see it will automatically generate the potential output file. So you can select this band structure. Here you can see the band structure has been selected. Then you can select this open. Now you can see the file has been selected. Then you can select this open. Then you will get the plot. So you can see this is the band structure.
So can you please repeat last 30 to 40 seconds?
Okay. Like whenever your input file will be completed. So if you want to plot the graph, you can see this is my input file. And if you want to show the location of input file and output file, just select any file, right click, select this open containing folder. You can see this is the location of my project. You can see these are the input file, and here we have the output file. So the same file location we need to import in the analysis plot. Like here you can see this is my device studio graphical user interface. So for plotting, you need to select the simulator, RESCU, select this analysis plot. This analysis plot you need to select. You can see this is my project location and this is my result folder. In the result folder, you can see band structure output file, real space density output file, density of state output file, and potential output file. So if you want to show the graph of any output file, like this is the band structure, you can see this band structure has been selected. Then you can click on this open, so that you will get the graph of the band structure. You can see this is the band structure plot with respect to energy. You can see these are the energy range. These are the high symmetry K point.
Hello, sir.
Yes, sir.
Excuse me, sir. Can we export this data in text or text format?
So this data is already in the text file. You can see this is the band structure output file in the text format.
If we copy the text file from this file in origin, the structure not looking the same. if we copy the data from this file and paste in an origin file, the picture or the presentation is looking the or for software and the origin both are different one.
Okay, like here you can see.
So open using origin, what you have to do is you just drag that file to origin so that the file could be imported.
I tried the same way, but I didn't
Okay.
open that file with same structure. They make
Mhm.
some other picture.
Did you
Like
plot graph?
Yes, I have to plot the graph.
Okay. Right.
Because we you have to write the we need the whole data in origin.
So when you import the file, what is the thing which you can see on the screen?
So
Wait,
can you share the screen, sir? Can you share the screen? And ma'am will help you to plot the graph.
wait. Is my share is
No, sir. Wait, sir. Yes, you can.
it my screen is seen?
Yes, yes.
I could
It's
see the
visible.
device studio screen. I couldn't see the origin screen.
Now
No, we could see only the device studio screen. We couldn't see the origin screen.
I have two screen. That's why.
All right. Okay, let me share my origin screen. You just check whether you are getting the
Okay.
same thing or
Okay,
something
okay. Show
else.
me your
Yeah,
screen.
yeah, sure. Is my screen visible?
Yes. Okay. Till now, yeah, till this, I also got in the same.
Okay. So now
Plot
what you
your
have to
graph.
do is you have to select and you have to plot graph.
Okay. Plot the graph, please.
Yeah. So here, sir, could you tell me like do we have two y axis and one x axis? Is it so?
Okay.
So now you just select and you have to plot like
This
this.
is like this is not. I think. Look here the in analysis plot. Your graph and this graph both are different.
Yeah, but it differs from the software.
Because this graph and that both graph are different. Looking the
Yeah,
different.
I could understand your point.
I am getting the same.
Okay, all right.
Sir, in the input file, we have defined the Spintronics application, that is collinear spin. So we will get the spin up data and spin down data. Here you can see.
What he is telling it, the structure of the graph differs from the device studio comparing to origin. That's what he is coming to tell.
Like in origin, they are plotting the both graph, spin up and spin down.
Okay.
Then how we can separate the graph in origin?
So just export this raw data in the text format. You can see then you will get the spin up and spin down. Here you can see this is the spin up and this is the spin down. So just export this data.
Or are in image format? For data is in image format. We need in text format.
Okay, just wait.
Hello, sir.
Yes, sir.
Sir, I plotted the data in MATLAB. Even in that, it is not looking the same as it looks in the software rescue.
Sir, wait 1 second. So you can see the same data has been plotted in the MATLAB. You can see.
In my
the
case,
blue
it
one
is
for
not
the-
looking like that. Yeah, I can see.
The blue one is for the spin up and the red one is for the spin down.
Okay. Can I share my screenshot?
Yes, you can.
Yeah. Actually, I'm sorry, it was my mistake. My MATLAB takes time to run, so it was some another data. I'm sorry.
Okay, sir. Nice. Because you can see in the MATLAB, I have get the same data.
Yeah, sir. Now I got the same data when I closed my MATLAB and opened it again. Yeah. Thank you.
So for the origin, I will check first, then I will let you know. Because
Okay.
I don't have any origin software in my
Okay.
system.
Okay. Okay, fine.
Hello, Deepak ji.
Yes, ma'am. Yes, ma'am.
In the band structure calculation, what is the x-axis? Means which point is which one? How to know that?
Like at the x-axis, we have the key point sampling.
Yeah, but it is showing some mark like that only.
So if you want to show, so you can just open this input file. And you can see first one is U, X, G, X, W,
Okay,
K.
okay, fine.
G.
Okay.
So basically this is the band structure plot. And if you want to plot this density of state, you can see this is the RESCU. Select this analysis plot. Select this density of state. And you can see this is the density of state with respect to energy. And this is the spin up data. If you want to show the spin down, you can see this is the spin down data. Similarly, you can plot both spin up and spin down. Also, you can see this is our Fermi energy.
Sir, excuse me,
Yes.
sir. Some of the paper, the spin up and spin up down data, they are exactly opposite each other. Then how to plot the spin up and spin down data?
So if you want to plot, like here you can see, from this Spintronics, we have selected collinear spin. And here we have defined the maximum value.
Okay.
So in this collinear spin, you will get the spin up and spin down.
Okay.
Here you can see the text file data is there in the 1 second. Like here you can see spin up and spin down. If you want to take the data for the only spin up and spin down, we have this text file in the nanodical. That is basically in the nanodical.
Same text file we needed for for band structure, that text file.
Yes, because here you can see it has already generated the band structure text file
Mhm.
for the both spin up and spin down. But if you want to like separate that data for the spin up and
Sir,
spin down,
I already
yes.
sent some WhatsApp image for the density of state on your WhatsApp, sir. I need that one, similar to that one. But I could not send the image on Google Meet.
So where you have sent the file?
On your WhatsApp.
No, sir, there is no image.
Oh, I think I sent by personal.
No, sir, I
sent
did
by
not get any data.
Okay, I would send. Need.
No, sir, I did not get any file.
Spin up and spin down.
So basically, this is for the different structure. Here you can see this is the
No.
complex structure.
Yes, complex structure. This is up, positive y-axis is up and negative axis spin down. We are getting only positive axis, spin up and spin down both.
Positive axis.
Here this figure shows the spin up.
In this graph, you can see the red one is for the spin up, and the blue one is for the spin down.
No. The red one is for the one structure, copper ferrous sulfide, and the blue one for the silver doped copper ferrous sulfide. From origin from this line to the up, say positive y-axis spin up and negative y-axis spin down.
So can you send me this file?
I sent.
So that I can simulate this structure. So that I think I will get that type of plot.
I think I read this paper. I don't have that file. I just read the paper. I need this one. That's why I'm finding. I sent the.
Okay, sir. No, so after this session, I will let you know.
Okay.
Like you can see in Nanowire, you can export the data for the spin up and spin down. You can see. I would like to save. You can see this is the density of state for the spin down. You can see this is for the spin down, and same I get for the spin up. So I hope you learn how to simulate any material based on the density function theory, and also how can analyze their various properties. So the same procedure you can follow for the any structure. Now I would like to define some DFPT parameter, and then I would like to create their input file, analysis input file, and then I will start the simulation. So if you want to analyze the properties from the DFPT method, so first you can import some material. So this time I would like to select this import online option. So you can select import online, and then you can define some chemical formula of the material. You can see this is the import online interface. So if you want to analyze the optical property of hexagonal aluminum nitride, then here you can search aluminum nitride. You can see this is the chemical formula of the aluminum nitride. You can enter and click on this search option. So you can see this is the aluminum nitride with different space group information. So you can select this aluminum nitride. You can see I would like to calculate this optical property for the hexagonal aluminum nitride. So first I can import this aluminum nitride from this import option. So you can import this aluminum nitride. Select this add option. So you can see this is our hexagonal aluminum nitride. So if you want to show this structure into center position, here you can see we have the center option. So you can click just center option so that this atom will be center position. You can see this is our aluminum nitride. And if you want to analyze the optical properties for this aluminum nitride, you can select this simulator. You can select this rescue. Then you can select this DFPT, density function perturbation theory. So for the optical property simulation, we need to select the simulator, RESCU. We can select this DFPT. So you can see this is the density function perturbation theory calculation for this aluminum nitride. This is the basic setting. You can see this is the task. In the task, you can see this is the Phonon band structure calculation. So you can click on this Phonon band structure. Then you will find Phonon band structure calculation, Phonon density of state calculation, Phonon band structure and Phonon density of state calculation, optical property calculation, and Raman property calculation. So you can select this optical property calculation. Here you can see the optical property calculation has been selected. Here you can see this is the simmering sigma, this is the resolution, this is the SCF method, this is the exchange correlation function, K point sampling, and you can see iteration control, basis set, spin type, and this is the optic parameter. So here you can define the optic parameter like damping factor and E field direction. So once you define the parameter, then you need to select this generate file. So that optical property calculation and their input file will be generated. You can see I would like to select this generate file, and here you can see this is our aluminum nitride rescue DFPT folder. Then it will generate 4 input file: SCF.input file, dielectric.input file, Phonon.input file, and optical.input file. So first we need to run the SCF.input file. Then you can run dielectric.input file, then Phonon.input file, and optical.input file. So you need to run the SCF.input file first. Again, you can run this dielectric.input file. Then Phonon.input file. Then you can run this optical.input file. So this structure will take some time to simulate this structure. Here you can see the SCF.input file has been completed. So in the queue condition, you can run all this analysis input file. You can see the dielectric input file also completed. And now this Phonon.input file is in the running condition. Now you can see the Phonon.input file has been completed, and now this optical.input file is in the running condition, and also this file has been completed. So I hope everyone has been generated the input file, and also they have run the simulation. So once your simulation completed, then you will get the output file. You can see this is the rescue log.output file. Select this open containing folder. These are the input file, and here we have the output file. You can see this is the aluminum nitride dielectric .mat file. You can see optic.mat file. So this .mat output file has been generated once the simulation completed. So once your simulation completed, you can select this optical.input file. So you can open this optical.input file. You can right click, select this open with. So you can see this is the optical.input file. You can see this is our project location. So if you want to plot the graph, here you need to write some script. You can see this is the location. I need to copy. And here you can include .mat. So I have written this script for this particular input file. So once you write the script, you need to save this input file. You can see the input file has been saved. So I hope everyone has been written this script for plotting the graph. So once you write, you need to select this save option so that the input file will be saved. You can cancel this input file. Again, we need to run this input file so that their graph will be generated. So we can run this input file again to plot the graph. You can see the file has been completed. So once the file will be completed, again you can open the project location. You can see this is the RESCU DFPT folder, and you can see the graph has been plotted. Like you can see, this is the optic plot for the dielectric function, refractive index, IR intensities, and photon energy loss. So you can see the output file has been generated in the MATLAB file. So in the MAT file, we need to import this file into MATLAB to show the graph. So these are the MAT file. So from this browse option, you can locate your project into MATLAB. You can see this is my aluminum nitride. I would like to select this folder. You can see this is my project location. C, user, Ravik, document, device studio project, hands-on rescue second session. This is the aluminum. Here we have this rescue DFPT folder. You can see these are the input file and these are the output file. Also, you can get the MAT file in the result folder. You can see this is the Phonon.mat file, SCF.mat file, optic.mat file. And here we have the figure for the, you can see this is the dielectric permittivity, refractive index, photon energy loss, and this is the IR intensities. So you can double click on any figure. You can see this is the dielectric permittivity for the real and imaginary part. You can see this is the dielectric permittivity with respect to energy. This is the dielectric permittivity. In the same way, you can double click on this refractive index. You can see this is the refractive index for the real and imaginary part.
Hello, Deepak ji.
Yes, ma'am.
Can't we see these graphs in Device Studio itself?
No, ma'am. No, ma'am. Because here you can see the mat file has been generated, and that mat file you can import into MATLAB so that you can show the graph.
Okay. Like earlier we saw the density of states graph and those
Yes, ma'am. Yes, ma'am.
there, but these cannot be seen here.
No, ma'am. No. This file you can
And
see in the MATLAB.
so, like you wrote the line for the MATLAB figure, can we write to export in JPEG?
JPG format.
Yes. I'm asking because currently I don't have MATLAB on my laptop. That is why I was asking.
Okay.
Okay, no issue.
So also you can import this file into browse. You can see this is my MATLAB. So just you need to create an account and you can use the open MATLAB. So this is basically for free for any user. So there is no need of MATLAB license. You can see this is my plot. We need to select and import into MATLAB. Because I have already told you that this software is written in MATLAB and C. So some of the file will open in the MATLAB.
Okay, fine. Yes.
Okay, so this is the reflective index file. And here you can see this is the IR intensities. So this is the IR intensities with respect to energy. Also you can see this is the photon energy loss. So I hope in this session you will learn how to simulate any material with the help of density function theory and with the help of density function perturbation theory. So here I have taken the simple example. So after this session, you can take your own example. Any complex structure you can take and you can follow the same procedure. you can generate their input file, you can do the simulation, and once the file completed, then you will get the graph. And also you can see this is our YouTube channel, so where you will get more video regarding the RESCU and the nanodical software. You can see this is the impulse technology. You can go to the playlist. You can see this is the device studio videos, QTCAD video, RESCU software, LDOS, nanodical, SetFOS, and Exabyte. So you can select this RESCU. You can see this is the optical property calculation of the hexagonal aluminum nitride. You can see this is the webinar. You can see this is the Raman spectrum calculation for the boron nitride, crystal, and benzene. Also, you can see Phonon band structure and Phonon density of state for the diamond supercell structure. You can see I have simulated multiple projects. You can see this is the diamond Phonon band structure and Phonon density of state. So you can see this is the diamond supercell structure. And here I have calculated Phonon band structure and Phonon density of state. You can see the graph. You can see this is the band structure plot for the supercell diamond structure. And also you can see this is the density of state. So this is the Phonon density of state with respect to energy.
Excuse me, sir.
Yes, sir.
Can we export the same data from MATLAB to the text file?
So this is Phonon band structure.
Huh?
Here you can see this is the file option. Select the save as. Here you can select the file. I think text file is not there.
Can we export from? Can we export the same file?
Sir, here you can see the text file is not there. So BMP, EPS, JPG, PCX. So this file format you can export.
Okay. We will find the solution for how to extract the data from MATLAB or into the text for origin.
Okay, sir. So these are the videos. And for the theory and tutorials, you can visit our this Nano Academic. This nanoacademy.com you can visit, and here you will get the document and tutorial. And the hands-on training on the nanotical I will cover tomorrow. So if you have any query regarding the RESCU software, so you can unmute your mic and ask me the queries. So whatever the query you have, you can ask. I will try to help you. And after this session, you can simulate your own structure. And if you are getting any error, then you can let us know so that we can help you.
Excuse me, sir.
Yes, sir.
I have calculated wrote the program for nickel oxide for density of state and the band gap, and the plot already sent on the group.
Okay, we already sent it. Okay, 1 second.
Okay, that one, this one.
This one.
I need the same data for origin and same plot.
Sir, origin software, I will check that because I don't have any origin software.
Okay. That's why I got the good result for nickel oxide, but I'm not able to open the data in origin. That is my first question.
Okay, sir. So I will check that.
Second question is, people have to make some doping.
Okay.
Doping. How to add the doping in a crystal structure?
So you can see, doping is possible from this nanotical software.
In RESCU is not possible.
Yes, RESCU is not there.
Okay.
From this nanotical, it is possible. Like you can see, this is the virtual crystal approximation, and here we can include the doping. So this nanotical software and their demonstration I will cover tomorrow. You can see p-type doping, n-type doping. This is for the mixer vacancy, and also we can mix any atom in this structure from this add option.
Sir, can we have alloy, not doping, but alloys, like two different materials together?
Yes, we can. So like, can you suggest any material?
For example, platinum ruthenium.
So I need to check that file is there or not. But alloy is possible in this device studio.
But how to do that? Any guidance on that?
Platinum
and ruthenium.
I think this file is not there in the importer, so we need to
from online we can do, right?
So can I cover this tomorrow?
Yeah, sure, sir. Also, sir, like when you are going to explain about the IV characteristics, so can we also discuss about the adsorption properties? Like suppose we consider an alloy and then we talk about their adsorption properties. Is it possible to get it calculated from the current software?
No, ma'am, adsorption is not there, but we have another software that is StatFoss.
Which one, sir?
1 second. So you can see this is our StatFoss, so that we can calculate the absorption property, drift diffusion properties, advanced optics, and emission properties.
Okay, from StatFoss we can do that.
Yes.
And
Hello, sir.
also, when
Can
we
you
are talking about platinum and ruthenium, just 1 minute, sir, last question. Like you said, you will be guiding us about it tomorrow. I just
Yes,
want to know that when we are talking about the alloy, is it also possible that we can vary the composition, like, like number of platinum atoms would be 10 and we want ruthenium as 5, and then
yes,
go on like that?
yes. You can vary the composition.
We can vary. Okay. That's it, sir.
If
Thank
you
you,
want
sir.
to
I
change the
look
value.
forward for tomorrow's session.
Okay,
Thank you
no
so
worries.
much, sir.
Okay, thank you.
Hello, sir. Can we also please discuss regarding like how can we plot it in origin tomorrow?
Yes, sir. Tomorrow I will check that. I need
Yeah,
to
yeah.
check today evening, and tomorrow I will cover that.
Okay. Thank you, sir.
Hello,
Yes, ma'am.
Deepak ji, what will be the typical cost of this software?
Like when we have multiple options, like we have the 1 year license, 3 year license, 5 year license, and permanent license. And
Okay.
for the
So,
single user as well
huh.
as multiple user, like 5 user, 10 user.
Okay, for single user
So if you talk
and
about
1 year,
so regarding the nanodical or rescue license, ma'am, are you talking
both,
about both?
both.
Okay. So if you talk about the both license for the single permanent, then the price will be 6.5 lakh plus GST.
Okay.
So both license you can get for single user permanent 6.5 lakh.
Okay. And for rescue only?
So if you go for the rescue only permanent license single, then the price will be 4 lakh plus GST. And if you go for only nanodical license, then the price will be 5 lakh plus GST.
Okay.
And sir, what about ZFOS?
So in this at first we have multiple module, like you can see. We have the absorption module, drift diffusion module, advanced optics module, and emission module. So the price depend upon the module, like which module you want to work.
Sir, in this, I could see now it is absorption. I am looking forward for adsorption.
Okay, so ma'am, I need to check the point for this set for software.
Yeah. All right, sir. I'll wait.
Deepak ji,
Yes, ma'am.
do you provide this through GEM link also? Because I belong to a government organization and purchasing is through GEM only.
Okay. Okay, ma'am, no issue. We can discuss on this.
So I will mail you, in fact.
Okay, ma'am. Okay,
That
no
will be
issue.
better so that we can discuss in detail.
Yes, yes.
Yeah. Okay. Okay. Thank you.
Okay, ma'am. Thank you so much. Yes, and definitely we will provide you the recording session of this hands-on. Also, you can see multiple videos are available for the hands-on. You can see. So after this 2 days, we will upload on the YouTube. So from my side, thank you so much to all of you for joining this session.